Hi, welcome to maths class. Today we're looking at differentiating the exponential function. And the exponential function is one of the most special functions because, and I know we've discussed this before, it is its own derivative, which means that if I start with f of x equals e to the power of x, that's my exponential function, then I want the derivative, it's the same function. If I graph them, one of them will sit exactly on top of another. It's slightly different when I have a constant multiplied by x there, such as e to the kx. When I find the derivative there, I bring the constant out the front. The derivative is k times e to the kx. So what I'm going to do now is I'm just going to take you through two short worked examples to show you how to use it. My first example is y equals e to the power of negative 5x plus 2x squared. So because I'm starting with y equals, I'm going to use dy dx notation to talk about my derivative function. So I take the constant negative 5 here, I multiply it out the front. Then all I do is I keep what I started with. I started with e to the power of negative 5x, I've still got e to the power of negative 5x. That bit's easy. The next bit's also easy. 2x squared, I take this 2 out the front and I multiply it by the 2 that's already there to get 4x, and I'm going to subtract 1 from that power, which gives me a 1. I won't write it. So I've got negative 5e to the power of negative 5x plus 4x is the derivative function. All right, example 2 looks a little bit different, and that's because what I have here is a composite function. I've got e to the power of another function, and that function is 2x squared plus 1. I could rewrite this as e to the power of u if I say let u equal 2x squared plus 1. So the key here to answering this question is identifying that what I've got is a composite function and that this here is the inside function and e to the x is the outside function. Now, the other thing I need to do is, because I'm going to use dy dx notation, I'm going to start by saying let y equal e to the 2x squared plus 1. Then if I define u equals 2x squared plus 1, I've now got y equals e to the u. And my next step is to differentiate both of those. dy with respect to u. Now, e to the u, it's its own derivative, e to the u. Nothing happened at all. And with u, I need to find du dx, and that gives me 4x. The 1 has a 0 derivative because it's a constant. So now I'm going to apply my chain rule. Dy dx equals dy du times du dx. And what I get here, dy du is e to the power of u times du dx is 4x. This gives me 4x times e to the power of, instead of u, I'm going to replace it with my 2x squared plus 1. Now, what I want to point out to you here is that once I have found the derivative of my original function, does it all fit? Hang on, if I can squeeze it all in. I'll rewrite this solution here. Dy dx equals 4x e to the 2x squared plus 1. Now I can fit it all in. My original function was e to the 2x squared plus 1. My original function is still here. And what I've done is I've multiplied 4x times this, and 4x is the derivative of this. So in actual fact, if I started with f of x equals e to the 2x squared plus 1, then the derivative of that is simply the derivative of this, the 4x part, times f of x, which is what I started with. Okay? So my derivative is 4x e to the 2x squared plus 1. And that's finding the derivative of the exponential function.